Hi everyone, thank you for joining us today. My name is Kevin. I'm the Director of Marketing at Unchained Labs, and I'll be your moderator today. During today's live demo, we'll be taking you through a walkthrough of how to use UNCLE for isothermal testing of protein stability. But if you have any questions, you can enter them by hitting the Q&A button at the top or bottom of your screen in the Zoom navigation bar. We'll handle those during the Q&A session at the end of today's live demo, but please enter them in at any time. First, I'd like to introduce Andre. Andre is our UNCLE product manager who will be taking us through that live demo of UNCLE, and we'll be checking out how to use UNCLE for isothermal stability testing of proteins. So, Andre, take it away.
Thank you, Kevin, for the introduction, and thank you all for joining me this morning for the live demo in which I will introduce you to isothermal testing in UNCLE. I will introduce the instrument first, then I will show you how the samples are put into the system using our sample holder called the UNI. Then we will set up the experiment and we will go through the analysis steps. Before starting with these technical details, I want to spend a little bit of time talking about isothermal testing. When you have proteins and you want to characterize their stability, you have several ways of doing this. You can look at how the protein behaves in a thermal ramp. You can determine things like the melting temperature and the aggregation temperature. That is very important information, and these thermal ramps are usually pretty fast experiments in the order of something like 2 hours. But in order to understand the full stability picture, it's also good to take a look at isothermal stability. So keeping your sample at a given temperature over several hours, several days, maybe several weeks, and looking at how does aggregation, how does unfolding behave over that longer period of time. So the aim of isothermal stability testing is to add to the full stability picture of your analyte. Isothermal testing used to be kind of a cumbersome process. You would store your sample, you would take aliquots out, you look at how much aggregation is in there by methods like HPLC, for example, but it was all in all a lot of work. And we thought that UNCLE is a very convenient way of testing isothermal stability with a range of between 1 and 48 samples at a time, and that's what I'm going to talk about in this live demo today. First of all, the main player of the show, UNCLE, our all-in-one protein stability platform, measures 3 different modalities of your sample. Measures the fluorescence, the static light scattering, and the dynamic light scattering. By looking at the fluorescence, we can gauge the unfolding of the protein. This is, of course, one very important stability metric. Static light scattering is a function of the molar mass of an analyte. So by looking at how the molar mass determines how we can gauge aggregation of the sample over time or over a temperature gradient. The DLS, the third measurement modality, is an orthogonal measure of size of aggregation. We're looking at the diffusive properties of the analyte, and we get to a parameter called the hydrodynamic diameter. So looking at aggregation by 2 metrics, DLS and SLS, and looking at unfolding with fluorescence. That's what UNCLE does. UNCLE does this, as I was mentioning, a number between 1 and 48 samples, and it is a temperature-controlled environment inside the instrument. I'll show you the inside later. You can set the temperature between 15 and 95 degrees for isothermal experiments, and you can ramp them also for your thermal ramp. Before looking at how to set up this isothermal experiment, let me show you how to introduce the sample into the UNI so we're ready to start our experiment. Let's walk over to the close-up of the UNI. This is our UNI. It consists of several components. First of all, we have this black anodized aluminum frame with 16 quartz cuvettes. These quartz cuvettes are open at both ends, and they have a filling volume of 9 microliters. We have silicon gaskets, and we have a reusable aluminum frame in blue. These gaskets go into the frame like this, and they will then seal these open capillaries on both sides, these open cuvettes on both sides, so that we don't have to worry about liquid evaporation and loss of sample. They'll be safely sealed between those silicon gaskets. We give you silicon gaskets for every UNI that you get from us so that you can exchange them after every experiment, and you make sure there is no cross-contamination. The nice side effect of having the sample in this sealed frame is also that you can carry it around and don't have to worry about loss of sample or contamination or cross-contamination. So in order to load our cuvette, we use this aluminum block tool. The UNI clicks in place here. It's held in place by magnets, and it's positioned that way as well. And then we have these helper lines here that help us load. So let me get my pipette ready and some 1x PBS. So nothing hazardous here, just PBS. That's why I'm not wearing any gloves. Aspirate 9 microliters of sample. and then load the cuvette like this. Capillary force basically wicks the sample right into the cuvette, and it's really, really easy to load. You can put the tip of the cuvette, the tip of the pipette into the cuvette if you like, but as I said, capillary force is your friend. Then when your samples are loaded, you take this frame like this, and then close it, close the metal latch on the side, and then your sample is ready to go into Uncle to be characterized. Let's walk back to the instrument so I can show you how to set up the experiment. Okay, in order to set up an experiment, let me share my screen here. So Uncle software consists of two different components. We have Uncle Client and Uncle Analysis. Uncle Client is the part of the software that controls the instrument and controls data acquisition. Uncle Analysis, which we'll look at later, of course, as the name suggests, is used to analyze your samples. When you boot Uncle Client and you log in, you are presented with this screen in which you can then select the applications. Today, we're focusing on isothermal applications, so we're going to open our isothermal stability toolbox. All in all, just to point out, we have 15 different applications in here. Today, the focus is going to be on whatever is included in the isothermal stability toolbox. You see there are 3 applications in here: isothermal, isothermal using Cipro, and out-of-the-box stability. Isothermal is, as the name suggests, the app that we're going to use today for isothermal characterization of your sample over at a given temperature over longer periods of time. If you want to focus on the fluorescence of a reporter dye like Cipro Orange, you can use the application isothermal using Cipro that is tailored for the use of the reporter dye, uses only one of Uncle's laser systems to excite fluorescence, whereas in isothermal you have the choice between both for protein intrinsic fluorescence and also for reporter dye fluorescence. In the first half of the demo, we'll look at isothermal application, and in the second half, we'll take a look at out-of-the-box stability. I'll talk a little bit more about that later, so get excited. When you choose isothermal, the application you want to use, we first have to choose a project. It's going to be the live demo project. You can name your run here. Let's call it live demo September, because it is September, right? And then we need to select our samples. I have already populated a set of 8 samples for our live demo here, because what we're going to be looking at today is a monoclonal antibody in 4 different formulations. We have a slightly acidic phosphate buffer, 25 millimolar phosphate at pH 6.1. We have a neutral, or more neutral phosphate buffer at pH 7.4. We also have a histidine buffer, slightly acidic, 6.4 is the pH here, and histidine 7.4. And then also the buffers here alone as our blanks. In order to graphically populate the unis so that the software knows which sample is where, you can click your sample and drag it over like this. Let's put 4 of our blanks in here first. And then when you want to run your sample, let's run our first sample in triplicate. You choose the first cuvette you want to populate. Have 3 replicates here. I click replicate, and then 3 of them are going to be populated. Same thing with more neutral phosphate. And then we take the histidine first, and then the last one, and then all, as if by magic, our full uni is being populated, and we're ready to move to the next stage of experiment setup. That will be to set the parameters of our experiment. In our isothermal experiment, we can choose to use fluorescence and SLS and or DLS. So you can do DLS only this way, or you can do both. But for this show and tell, let's do the full data acquisition. The first section here is the DLS acquisition parameters, so number of acquisitions and also the acquisition time. Down here we choose temperature, the pre-measurement incubation time, and then we can also choose if we want to set this experiment up as a number of repeats, so want to run SLS, DLS fluorescence here 5 times, or you can set the maximum number of seconds you want to set, for example, to set this up for a whole week. When this is all set up and you like all of this, you can click apply down here, which takes you to the screen to load the samples. Load the samples into Uncle, hit start. I will show you the detailed steps in the second part when we talk about the out-of-the-box experiment. So let's take a look at some isothermal data that I've recorded. The thing with isothermal experiments is they take quite a bit of time. So what I did last week is I recorded 24-hour incubations of our analyte in the 4 conditions mentioned at different temperatures. So if we look at the first incubation temperature, I started pretty safely. I started at 37 degrees Celsius. The results look like this. So we're looking at the graph over here shows the signal, the static light scattering signal recorded at 266 nanometers. So that's our most sensitive aggregation measure. And we have in green, we have the monoclonal antibody in the neutral phosphate. In purple, we have it in the neutral histidine. And then we have the 2 acidic ones up here. You can see that in the acidic conditions, the static light scattering signal is a little bit higher, indicating a little bit of aggregation. But all in all, over the 24 hours that this experiment ran, you see the x-axis here is time in thousands of seconds, overall 24 hours long. There is a slight increase in the signal, but it's not very much. I did measure not only static light scattering, I also measured dynamic light scattering. And if we look at that for the same samples, we can see that the hydrodynamic diameter is the usual one that you would expect for an IgG type molecule, monoclonal antibody that we're using here in this case. So it starts at a value of about 11 nanometers, and it remains in that range until the end. So at 37 degrees, 24 hours, this protein is very stable in all 4 conditions, and not much aggregation occurs. I edged my way up by 5-degree increments, so from 37 to 42 to 47, and now let's take a look at the 52-degree incubation. In the 52-degree incubation, we see something happening in 2 of the conditions. The colors are a bit different from the experiment before. So in this case here, we have our sodium phosphate, the neutral sodium phosphate down here in this purple tone. We have orange, that is the histidine, and we have the light blue, that is the histidine in acidic, and then we have the phosphate in acidic. And you can see that in the lower pH conditions, the static light scattering signal increases quite a bit over our 24-hour incubation. Taking a look at a second metric here, the dynamic light scattering metric. Let me move over to that. Now my zoom bar is at the top or bottom of the screen. I have to move it away so I can click here. If you look at our DLS, that confirms what we saw for SLS before. So in case of the neutral ones, the diameter remains flat. There's not much there's no aggregation occurring. But in the more acidic conditions, we see that the radius, the diameter increases to a value of peaks out at about 74 nanometers. So from 11 nanometers starting point for an IgG type molecule all the way up to 74 nanometers. So significant amount of aggregation occurring here in this case. I didn't stop at 52 degrees. I went further, 57 and also 62. And I want to show you what I found for 62 because that's a pretty interesting result, I think. We look at the static light scattering signal here, in this case only the acidic pHs, and you can see how the static light scattering signal increases, peaks at about, 18,000 seconds. That's about a quarter in, so about 6 hours later, and then the signal starts decreasing again. This salmon pink color here is our sodium phosphate. Looking at the histidine down here, the peak happens a bit earlier, so it already happens at about, 2-3 hours in, and then the signal decreases again. Static light scattering is proportional to the molar mass and also the concentration. So in case the static light scattering signal decreases, it can either mean that the aggregates are falling apart or that they precipitate, so the concentration drops. Is there any way we could possibly differentiate between those 2 phenomena? And I think DLS can come to the rescue here. If we look at that, we can see that for both conditions over 24 hours, the aggregates remain. So it's still 56 nanometers here in diameter at the end, or even 75. So the aggregates are obviously not falling apart. The aggregates are still present after 24 hours. DLS shows us this. So the decrease in the static light scattering signal is due to the sample precipitating at 62 degrees over 24 hours. So with that, or this example of looking at this monoclonal antibody in 24-hour isothermal incubations at different temperatures, I think I could show you how versatile the characterization uncle is, where you can look at your aggregation in static light scattering, in dynamic light scattering, and you can also look at the fluorescence signal to find out how the unfolding behavior of the protein is. I have, of course, not shown you yet how to put your sample into the uncle. I will show you this in the second part that starts now, where I'm talking about the out-of-the-box experiments. The thinking behind the out-of-the-box experiments is that an isothermal experiment takes quite an amount of time. We are incubating the sample for 24 hours, 2 days, 3 days, a week, and that means uncle is going to be tied up in that experiment. You might want to use uncle for other things as well. So you might want to do a thermal ramp, you might want to do a capsule stability test, you might want to do a viscosity measurement in uncle, all of these things at the same time. And that's where the out-of-the-box experiments come in, because, as the name suggests, you incubate outside of the box. You take your sample to uncle, you record data, then you take your sample out, incubate it in an incubator outside of the box, outside of the uncle box, and you bring it back in for more data acquisition. So it's a discontinuous experiment, and you choose the intervals between that, and that way you can keep the instrument available for other short-range experiments like a thermal ramp. When you set up, let me do this again because it was kind of quick. So we go to the isothermal stability toolbox, we choose out-of-the-box stability, and then the first thing the software asks you is, are you starting a new experiment or are you continuing an existing one? Let me show you how to set up a new experiment. Again, we go into the live demo. We call this one out of the box to differentiate it from the previous one, OTB, out of the box. And then again, we take our samples, populate our uni this way. I'm just going to put in 2 samples now because you've seen me do this before and it's not the most exciting thing to watch. And when the uni is populated, you click Finish. You set your, again, like before, choose what measurement modalities you want to use, static light scattering and fluorescence, and or DLS. You choose the temperature. Let's put in 25 degrees here for now. And then when everything is ready to go, you click Apply, and now it's time to load the samples. Once I hit this button, you'll hear the door opening, and we'll change camera's perspective so you can take a look into the instrument, and I'll show you how to insert the uni. When the door opens, you saw it slides away to the left, and then you see the hot plate, the tray come out. This is a straylight cover that we use to put on top of the unis. I have the uni that we loaded before. Here, I'm going to put it in position number 1. You can put 1 uni, 2 unis, 3 unis in there. Each one has 16 samples. That's how we get to 48. Mathematics is beautiful, isn't it? And this copper plate here is the actual hot plate. That is the temperature controlled part. The uni, the aluminum part, has direct contact with it, which leads to quick thermal equilibration. And as you could hear it click into place, the same magnets that I used earlier to put the uni into the loading tool are also holding the uni in the right position here on the hot plate. I'm going to return my straylight cover and then go back to the instrument to close the door. Let me share my screen again here so you see what I'm doing. So our uncle asks us if we would like to set the instrument to starting temperature. Yes, of course. And then we'll close the door. You can hear it close. And then because the default temperature is 25 degrees, I chose 25 degrees. This equilibration will be pretty quick. And then the next thing I want to show you is the last part of setting up the experiment, that is to choose the acquisition settings. If you choose your acquisition settings, you are taken to a screen like this. Right now we're looking at the fluorescence and SLS screen. There is a corresponding screen for DLS as well. And now I know that there's a protein in sample B, so I'm going to use trigger down here to expose the sample and see what the fluorescence output is. We can see a pretty nice output here, almost 25,000 counts. That's quite intense. I think I'll use a different filter setting here to let a little bit less exposure to the sample. because we are, after all, planning an isothermal experiment, so it's going to run over some time, so the signal will probably go up. We don't want to start with a very high signal. We want to start a little bit lower, so we have room to go up in this. And I think something like 10 to 12,000 is good. So in this case, then I could hit start, and that would start my data acquisition of my first OTB data point. When the OTB experiment is finished, UNCLE will remain at temperature, which is important because if you imagine you are incubating something at 60 degrees, you want the sample to remain at 60 degrees until you're ready to take it out, take it to your incubator and continue incubation outside of UNCLE. When you then go back to you record your second data point, you go to out-of-the-box stability, and now you choose to continue an existing experiment. All the parameters you set the first time are still going to be in, and of course you want to set you want to run your OTB with the same parameters in every data acquisition, so everything is shown to you, so you know what you set, but you can edit those, and then you can add the next data point and the next and the next, and so on. The result of an OTB experiment looks like this. So this was a freeze-thaw experiment. So I took our monoclonal antibody, NPBS, measured it at time point 0, went to a freeze-thaw, measured it again, another freeze-thaw. This one was over the weekend. As you can see, the gap is wider in between the two data points, and then another third freeze-thaw as well. And then the points here are the results for a 2 milligram per milliliter solution and a 1 milligram per milliliter solution. They both agree in that our static light scattering signal is pretty constant, pretty stable after the first freeze-thaw cycle, the second freeze-thaw cycle, and after the third freeze-thaw cycle, it starts aggregating. So this sample is safe in PBS without any additives for 2 freeze-thaw cycles, and then it starts aggregating. We, of course, also have the option of recording DLS in the out-of-the-box experiment, and this one confirms. This is one of the 2 samples shown here. This is the 1 milligram per milliliter solution. We start at about 11 nanometers in diameter. After the first freeze-thaw, it goes up a little bit, second freeze-thaw, and then we really, after the third freeze-thaw, we see a significant increase in the diameter of our sample. So DLS, again, confirms SLS. We have the option of looking a little bit more closely into the diameter distributions in UNCLE software here. Double-click on the sample, and we can see that start here. So in the beginning, we have intensity distribution nicely centered around 10 nanometers. And then as the experiment progresses, we'll see larger radii or larger diameters show up as well. In the mass distribution, we see that these are not very prevalent. It's less than 0.1% of aggregate that's forming. But static light scattering is very sensitive in picking up on this. And looking at both the SLS and the DLS signal for the sample will show us very obviously what's happening and how much aggregation is actually happening. This would be what I wanted to show you today for the out-of-the-box experiments. This was a freeze-thaw experiment, but you could also use this for higher temperature incubation. UNCLE is, I think the hallmark of UNCLE is really that it's a very flexible instrument. You can use it to focus on different aspects of the fluorescence, and you can also use it to look at the isothermal in the box, out of the box, and also use it for 14 other applications. I'm going to stop sharing my screen, and I think now it's time to take a look at some questions.
All right, Andre, thanks for that excellent presentation on how to use UNCLE and walking us through both the isothermal applications and the out-of-the-box applications. So 2 very cool new use cases for UNCLE there. We have a bunch of questions coming in, so I will just start from the top and go from there. So first of all, we looked at those new isothermal applications in UNCLE 6.0. What else is new in the software?
So UNCLE 6.0 was released in late July, and we always listen to feedback from our customers and see what features they would request from us. One thing that we implemented in the new version, in addition to the bunch of isothermal applications, is to show replicate groups. So if you run a sample in duplicate or triplicate, UNCLE is able to show you the average value and also standard deviation. So you can, of course, always export things and do this in Excel, but now you can look at the average already in UNCLE software. We also extended advanced analysis, so gave you more flexibility in the analysis wavelengths that you use in the analysis portion of the software, and generally also gave the software a facelift. So it looks and feels a lot more streamlined now, and it is smoother to use. So it's fun to use. If you used 5 before, I think you'll like 6.
All right. Thanks for that nice overview. So next question here, pretty interesting one. Besides screening for formulation, can you use the isothermal experiments to screen for optimal protein concentration in your formulation? So instead of looking at formulation, thinking about protein concentration.
Yeah, I think so. I mean, I think the one thing that we wanted to give people with the isothermal application is a lot of flexibility. You can use the isothermal application to screen a bunch of different constructs. You can use the isothermal application to screen a bunch of different formulations, but you can also use one formulation and look at different concentrations because, I mean, I showed you 1 and 2 milligrams per milliliter, which were almost the same in the example I showed you, but there's totally also conceivably an issue or an influence of the concentration on the aggregation behavior. So I think that could be a really cool application as well and use the platform, the stability platform that is UNCLE to take a look at this specific question for sure.
Yeah, I agree. So isothermal applications, we're thinking about, time is on the x-axis. Can UNCLE determine rate constants in those isothermal applications?
Yes. I didn't go into detail here when we were looking at the data before, but you could see the individual data points and then lines. Those lines are fit lines. So UNCLE uses exponential fits, phased exponential fits, and we can cope with monophasic behaviors, biphasic and triphasic behaviors, and the software will determine the rate constants for those individual segments as well. So there's not only this line is higher than that, there's actually also a mathematical parameter that the software determines that it lets you compare different conditions and different experiments.
Okay. And then another question, this one, maybe from a current user, asking more about the setup of isothermal experiments. So specifically talking about what is the hold time and the use repeats when setting up that experiment, but maybe just walk through, how you set those up, what parameters you can control.
Right. The isothermal experiment is keeping the sample at a given temperature over a longer period of time. So the easiest way of setting it up is just to say, let's run this for the amount of seconds equivalent to 7 days. So do the maths and put it in for that many seconds. And then the system will just be measuring again and again and again and again until the week is up. That can mean that your sample is exposed to UV light quite a bit. That's where the hold time comes in. The hold time is the delay between repeat measurements of the same well. So if you say hold time of 1,000 seconds, when the measurement comes back to well A1, it will wait until 1,000 seconds have elapsed. That way you can stagger your measurements out over a longer period of time. And especially when you use a reporter dye, you don't want to overexpose it to the laser and use the hold time for that. If you are just interested in reading 5 repeats, you don't use the time to determine the duration of the experiment. You can just say, I want 5 readings done at 48 degrees, and that's where the repeats come in. So the setup is very flexible in that, and you choose if you want to go by number of repeats, or if you want to go by time, and also how you want to space out those measurements using the hold time.
Yeah, it's a lot of flexibility depending on what you're looking for.
Yeah.
So today we looked at applications for proteins and protein formulation screening. I know gene therapy is definitely a very hot topic right now. Can isothermal applications be used with AAV?
Yes, they can. When I showed you the 3 isothermal applications in the isothermal stability toolbox, I did not show you the 2 isothermal applications that we hid in the viral stability toolbox. So we have 2, an out of the box and a regular isothermal that are specifically tailored to the use with AAVs, with viral vectors, and just because topically they are viral vector characterization, we put them in the other toolbox. But there's a total of 5 isothermal applications, 3 for proteins in general, and 2 for the specific proteins that are viral vectors. So you can look at genome ejection in an isothermal incubation as well.
Yeah, and actually this question might dovetail nicely with those 3 applications. How about Cypher Orange? Using that.
Yeah. So that's the isothermal using Cipro uses only the laser system that is exciting the Cipro orange fluorescence and thereby keeps the experiment a little simpler. But yes, UNCLE's full flexibility of having 2 excitation lasers is also mirrored in the choice of isothermal applications.
Okay, all right. We're coming up at the bottom of the hour. We've got a few more questions. We'll go tackle those. If anyone has any additional questions, feel free to type those in the Q&A. But we'll see if we can get through these 3 before hit, the bottom of the hour. What concentration of protein is needed for UNCLE?
For a fluorescence experiment, it always depends on the primary structure. So the more fluorescent residues are in there, the lower concentration you can use. Let me give you, because I mean, of course, the answer of this, you want a milligram per milliliter concentration. Let's take the DLS as the example for our DLS measurement. we need about 0.1 milligrams per milliliter of IgG type molecules, so about 150 kilodaltons. That's also usually good for the fluorescence measurement. If your protein is very poor in fluorescent residues, you might want to have to go higher or use a reporter dye. But I think a good rule of thumb is 0.1 milligrams per milliliter or higher, so a very normal concentration for anybody working with biologics, really.
Okay. And then thinking about moving to regulated environments, does Uncle have tools for 21 CFR Part 11 compliance?
It does, yeah. We can qualify the instrument, installation and operational qualification, and we also have a 21 CFR Part 11 mode in the software that adds the audit trail, so gets you ready to be compliant.
Okay. And last one on my Q&A list here. Can you use unis for several tests?
Yeah, thanks for that one. So the individual uni cuvette is single use. There are 16 cuvettes in the frame, though, so you could use one today, the next one tomorrow, and the other 14 the day after. So the uni itself can be used several times, but every cuvette is designed for single use. Imagine you have a quartz cuvette, you have a protein sample in there, it precipitates, you have a coating on the inside. You cannot never clean it, get it back to the same optical quality. So the uni cuvette itself is single use. We give you enough silicone gaskets so you can seal those off. And also, I mean, in a way, every single experiment with a uni cuvette, you get so many data points out of it. So it is, in a way, reused in the experiment itself. But the cuvette itself is single use.
Okay. So that's the end of the Q&A that we've seen coming in. So thanks for answering all those great questions, Andre. And I want to thank you for a great presentation of Uncle as well. Also, thanks to our audience for joining us. If you want to have a deeper conversation with us, please don't hesitate to get in touch. You can reach us through our website, unchainedlabs.com, or through info@unchainedlabs.com. We'll be happy to connect you with your local scientists so you can talk more. We love having chats about science and what you're up to. Thank you again for attending our live demo, and hope you have a nice day.
Thank you.